This module is intended to provide the awareness, knowledge, skills and motivation required of shipboard and office-based staff on shipboard energy management techniques and activities. This module aims to provide the trainees with relevant information on the main shipboard energy efficiency measures, EEMS, technical aspects including engines, auxiliary machinery and steam system, fuel management, and technology upgrades. Upon completion of this module, you will be able to talk about the main shipboard staff and their roles and responsibilities, be able to provide a list of the main shipboard energy efficiency measures, or EEMS, be familiar with the general aspect of ballast water management and its relevant EEMS, explain issues of hull and propeller roughness, fouling level of impacts on energy efficiency, and options for monitoring, describe a typical shipboard steam system, relevant EEMS, and best practice for fuel saving. Discuss the fuel management aspect of energy efficiency. Describe a number of technology upgrades for energy efficiency for existing ships. A number of topics are covered, including 1. Typical shipboard organizational charts and the role of various individuals and departments. 2. An overview of main shipboard EEMS, their significance and potential saving levels. 3. Trim optimization, its impact and best practice. 4. Ballast water exchange and management and its relevant EEMS. 5. Hull and propeller roughness, fouling and its monitoring. 6. Engine and machinery performance and use management. 7. Fuel management aspects including storage, treatment and purification. 8. Ship maintenance aspects and the impact on energy efficiency. In this section, including the next few slides, information is provided on shipboard management structure and organizational chart, main roles and main departments. This section also highlights the main roles and responsibilities, in particular for those that have significant impact on shipboard energy management. The training of shipboard staff on energy management activities are highlighted in various IMO guidelines, and thus the initial effort by companies will include awareness raising and changes of shipboard culture with regard to energy efficiency. The ship's crew are the personnel who sail on board a ship and are responsible for its operation, primarily when the ship is at sea, with some responsibility for when at port. For the purpose of ship operations, and traditionally, the crew of a commercial ship is divided into 3 departments. 1, the deck department, 2, the engine department, and 3, the catering or steward department. The captain or master is the ship's highest responsible officer, acting on behalf of the ship's owner, operator, or manager. The captain or master is legally responsible for the day-to-day management of the ship. It is his or her responsibility to ensure that all the departments perform legally in accordance with the requirements of the ship's owner, operator, or manager. The chief officer or second in command plays significant roles on the cargo and loading-unloading operations, ballast water management, trim optimization, and aspects of hull and propeller condition and maintenance, among other duties. The chief engineer plays a major role on technical issues, including the maintenance, condition, and performance of engines and various machinery and the way they are utilized. The second engineer has the second most important role in the engine department by virtue of being the most engaged person in the engine department in the day-to-day operation and maintenance of various systems. One of the main issues observed most of the time is the lack of optimal organizational communications between various departments that can lead to a waste of energy. For example, communication between deck and engine departments is essential for the machinery use optimization. In an effective shipboard energy efficiency program, the collaboration and communication between all departments needs to be enhanced. This may be achieved through consideration of energy efficiency at daily meetings and through relevant shipboard work planning for the reduction of energy, compressed air, and freshwater use. This slide summarizes the energy efficiency measures relating to ship's operation and commercial management. Each of the measures will be explained briefly in the next few slides. The measures discussed begin with trim optimization measures and conclude with maintenance and planning systems. Most ships are designed to carry designated amounts of cargo at a certain speed for particular amounts of fuel consumption. The same applies to ballast operations, whether loaded or unloaded. For such conditions, normally there exists a ship trim that minimizes the propulsion power and thus the main engine's fuel consumption. For any given draft, there's one optimum trim that gives minimum ship resistance. In some ships, it is possible to assess optimum trim conditions for fuel efficiency continuously throughout the voyage. Setting the ship trim is to a large extent in the hands of the shipboard staff, although loading, operational, and navigational constraints may limit the proper use of this energy efficient measure. Ships normally carry ballast water to ensure a ship's stability and safety. Normally, ballast levels should be adjusted to account for requirements to meet ship stability, steering aspects of the ship, and the optimum trim. This does not necessarily mean carrying lots of ballast water all the time, as this can unnecessarily increase the ship's displacement and thereby increase fuel consumption. Thus, there is an optimum ballast condition that needs to be achieved through cargo planning as well as voyage planning. Optimizing the ballast levels for energy efficiency within the framework of ship's stability, steering ability, and optimum trim can be regarded as an energy efficient measure. The voyage should be planned taking into account when ballast water exchange can be carried out. Additionally, trim optimization and adjustments while in passage should be pre-planned in relation to the port normal even keel operation. Sediment uptake and removal should be controlled as part of voyage planning to ensure a minimum level of safety. The hull of vessels in a fleet is coated with anti-fouling system. In general, the smoother the outer hull is, the less will be the resistance, and therefore the vessel efficiency is improved. The effectiveness of hull coating systems would therefore largely depend on the level of maintenance and cleaning undertaken. Vessels in a fleet can be considered for application of self-polished coatings if this is not already occurring. Some of the main factors that influence hull fouling rates are the following: the initial roughness of the hull, the quality of the hull coating, the robustness of the coating with respect to mechanical damage, the areas of the hull where there is sunlight, the seawater temperature, the salinity of the water. The performance of coating will be a function of salinity of the water, the amount of algae in the water, the ship's speed and its operation profile, and hull maintenance. Regular in-service cleaning is beneficial if damage to coating is to be avoided. For partial cleaning, the priorities are the forward third of the hull and the remainder of the hull, working from forward to aft with emphasis on those areas which have most exposure to the light. The regular cleaning of macro fouling is highly recommended. For best results, The scheduling of cleaning should be based either on performance monitoring or on regular underwater inspections. Regular inspection, photographs, and roughness measurements are prudent ways to monitor the impact of cleaning and the condition of the coating. The use of underwater cleaning techniques and equipment should be done with care and with due consideration to original coating as well as to the amount of the fouling. For example, the removal of macro-size fouling is difficult to be done without the removal of a significant amount of paint. If anti-fouling is applied in different color layers, then these colors can be used to monitor paint removal during the cleaning process. Similar to the hull surface, propellers suffer degradation in performance due to surface roughness. The absolute magnitude of the reduction in ship efficiency due to propeller roughness is less than that experienced with a rough hull surface. However, it has been estimated that a rough propeller surface could still cause an increase of as much as 6% of total fuel consumption. Furthermore, the efficiency loss per unit of affected area is greater, making the economics of cleaning and polishing the propeller very compelling. Clean hull and propeller, as mentioned, can lead to significant fuel consumption reduction. Major questions are as follows. What are the optimal timings for hull and propeller cleaning? What is the best routine for cleaning to safeguard the existing paint system? What is the time and cost involved in applying a new coating, and which one should be chosen? Condition-based hull and propeller maintenance tries to give an answer to bullet point 1. This can be done in two ways. Measure and observe actual hull and propeller roughness and fouling, and compare with baseline values that indicate when cleaning should be done. You can use divers for this purpose. Use performance analysis packages that track changes in FOC, shaft power, and main engine power to identify degrading surface conditions. The concept of machinery load optimization and parallel operation reductions can be used for energy-saving purposes. On board ships, there are numerous instances when two machines may be used in parallel, both at low loads. The load profile for a multi-machinery setup can provide valuable information on methods of load sharing strategies and management between machines. In such cases, there is always scope for reduction of machinery usage through reducing their parallel operations. A ship's operations involve a variety of activities and tasks. Some aspects are as follows: loading, unloading, ballast and deballasting, inert gas generation and top-ups for crude oil product tankers, bunkering, maneuvering, standby, normal passage operation, waiting and anchorage, freshwater generation, portable water generation. The nature of these operations will vary from one ship to another. Also, operations may vary with areas, with the area of operation, and the ports of call. To improve fuel consumption, the requirements of various operations need to be carefully examined to ensure that the ship's machinery and resources are used appropriately. Planning the above requires good coordination between the deck and the engine departments. Covers the topic of fuel management. As an introduction to the topic, the following few slides highlight some of the key aspects and how they relate to the operation of ships to attain fuel consumption reduction. Fuel quality has a significant impact on an engine and a boiler's reliability and performance. When ordering fuel, qualities in terms of grade of fuel, its specification, calorific value and suitability for engines and boilers needs to be considered. It is well known that higher density fuels and higher water and sulfur contents all reduce calorific values that represents the energy content of fuel. Additionally, higher sulfur contributes to undesirable air emissions of sulfur oxide, and high metallic impurities put the engines and boilers at risk. Bunkers come in a wide variety of quality levels. In order to meet the international quality standards and statutory requirements, mainly sulfur, the marine residual fuels are generally blended by manufacturers or suppliers with different components. Using better quality fuel and/or a higher grade of fuel can lead to improvements in energy efficiency, safety of combustion systems, and/or prevent degradation. Furthermore, this will help to meet the regulatory requirements to reduce the sulfur level in bunker fuel. More and more refining processes and also blend components are being used, which could result in an increase in the levels of highly abrasive particles of aluminium and silicon, or a fuel's chemical stability over the long term. This has also raised concerns about the ignition and combustion quality of fuels, along with the issues related to the stability and compatibility of the fuels. The key points here are as follows. Avoid co-mingling. Do not mix different batches of fuel as far as possible. Note that incompatible fuels are the most common problem with the bunker fuel mixing that leads to clogged filters, engine damage, and other problems. Fuel additives are chemical compounds formulated to enhance the quality and the efficiency of the fuels used. Environmental legislation to reduce emissions and improve fuel economy is having a significant impact on fuel formulations and engine system designs. As a result of low sulfur regulations, the composition, the long-term stability, the lubricity, and the combustion quality of fuels are evolving due either to the desulfurization of heavy fuel oil or blending. Fuel contaminations with bio-related products mixed with fuels adds a new dimension to fuel's long-term stability. Additives could provide benefits for marine fuels primarily in the following areas: the improvement of fuel combustion, the reduction of particulate matter and visible smoke, the overcoming of soot buildup in the exhaust system, economizing improvements through keeping them clean, foul-free, with a reduction in the risk of fire, the reduction and inhibition of deposit buildup on piston rings, injector nozzles and valves, the reduction and prevention of cylinder liner lacquering buildup, and protection against fuel pump and injector needle seizures. An economical amount of bunker fuel should be carried. Energy is also used for temperature control of fuel and its transfer. To ensure energy efficient storage and transfer, fuel temperature in storage tanks needs to be controlled to the lowest feasible temperature in order to retain it in a fluid condition and also render it suitable for transfer. Ensure that tank fittings such as manhole covers and vent pipes do not allow water cargo or other material to get into the fuel. Ensure that heating coils are tight. Ensure that the tank wall condition is in good order, thus avoiding corrosion or other material being entrained with the fuel, which then has to be removed. Maintain settling tanks at a temperature which will enable the purifying heaters to achieve the required treatment temperature. When a surface tank is not in use, it is not necessary to maintain the usual high temperatures. Heater control should be checked to ensure correct operation. Accumulations of heater elements should be minimized. Periodically verify that the viscosity controller is working correctly. Monitor fuel oil sludge levels and ensure that sludge levels are not high due to poor maintenance of the purifiers. As advocated, homogenizers can be used to reduce the sludge levels. Fuel measurement and metering is the first step for subsequent performance analysis of various engines and boilers. The more accurately that fuel consumption is measured and reported, the greater will be the chances for identifying inefficiencies and making improvements. The International Safety Management Code, or ISM, specifies the rules and regulations for maintenance that influence the shipping industry. The ISM code stipulates that each ship's operator is responsible for the safe and pollution-free operation of the ship, and that the ship's hull, machinery, and equipment should be maintained and operated in accordance with applicable rules and regulations. The part of the ISM code on the maintenance of the ship and its equipment describes in general how ships should be maintained, inspected, non-conformities be reported, and corrective actions taken. Accordingly, the ISM code states that the shipping company should establish procedures to ensure that the ship is maintained in conformity with the provision of the relevant rules and regulations and with any additional requirements which may be established by the company. Based on the ISM code, it is a requirement that the company should identify equipment and technical systems that through sudden operational failure might result in hazardous situations. The shipping company usually chooses the most appropriate maintenance type for various ships' equipment based on its maintenance policy or strategy. The diagram above indicates different types and policy options. These are outlined in the next slide. Unplanned maintenance. This type of maintenance is basic and simple as it is defined as breakdown maintenance. In this maintenance policy, the repair or replacement is performed only when failure occurs. In this type of maintenance policy, however, basic preventative maintenance routines such as lubrication and machine adjustments are applied to the system at regular intervals. Planned maintenance. Maintenance scheduling or planning embraces all activities necessary to plan, control, and record all maintenance operations. Planned maintenance is based on a defined schedule of equipment maintenance. This maintenance is usually defined by the majority of shipping companies. The planned maintenance schedule is decided based on manufacturer's recommendation or use of analytical techniques such as analysis of mean time between failures, or MTBF, and reliability analysis. Preventive maintenance. This is a subset of planned maintenance. Preventive maintenance usually depends on the manufacturer's recommendations and past experience for scheduling repair or replacement time. Preventive maintenance is time-driven in that maintenance is performed based on elapsed time or hours of operation. Predictive maintenance. This is generally based on what is referred to as condition-based maintenance, or CBM, or reliability-based maintenance, RBM. The maintenance decision is based on the current condition or reliability of the system or equipment. Good maintenance is fundamental for energy-efficient operation of machines and systems. As has been discussed, maintenance of the hull, propeller, and main engine are very effective for energy efficiency. Thank you. This slide completes the current module.